So imagine you're the back office manager of a really busy restaurant, right?
Yeah, right. Well, on a Friday night or something.
Exactly, a busy Friday night. And you suddenly march out there and demand that all the waiters just stop taking orders for a second.
Just completely halt the floor.
Yeah, just so you can sit there and count the receipts from earlier. I mean, the restaurant would just completely collapse, right?
Oh, totally. The customers would riot.
Right. And, well, in the world of big data, preventing that exact kind of collapse is literally a multi-million-dollar engineering problem.
It really is. And, solving it requires this level of architectural thinking that I think most people just never get to see. You have to build these systems that allow for massive, really heavy analytics to happen completely seamlessly in the background.
While the live app just keeps running.
Exactly. Well, the live, real-time application just continues to function flawlessly for the actual end user.
Which brings us to our mission for you today in this deep dive. We actually got our hands on this really fascinating set of personal interview preparation notes.
Yeah, these are incredible.
They really are. They're from a big data architect. And we are talking about someone with over 13 years in IT, with the last half decade or so heavily specialized in big data and the Google Cloud Platform, or GCP.
That's a lot of specialized experience.
It is. And reading these notes, I mean, it kind of feels like stumbling into the private, I don't know, grease-stained notebook of a Michelin-starred master chef.
I love that analogy because you aren't just getting like a list of ingredients here. You're getting the underlying philosophy of how they actually keep the kitchen running under intense pressure.
Right, they're real secrets.
Yeah. When a professional with that much tenure sits down to synthesize their experience, they naturally filter out years of noise. They just deliver these absolute highest density insights.
Totally. And the most striking thing right off the bat is how this architect prepares for that classic, tell me about yourself interview question.
Oh, yeah, the dreaded first question.
Right. But they don't just dump a list of tools on you. I mean, sure, Airflow, BigQuery, Spanner, Python, those are all in there.
They have to be.
Yeah, but the entire focus of their introduction is on the actual business problems they solved. Like, they specifically highlight building a consent management platform and reducing false SLA alerts and running credit card defaulter analytics.
And see, that mindset, that dictates the entire architecture they build. Because, junior developers often focus on the mechanics of a specific tool. Right?
Oh, for sure. How do I write this code?
Exactly. But architects focus on the outcome. Solving those complex business problems at scale, like processing credit card defaults across, millions of users, it requires isolating different types of data chaos so they don't just destroy each other.
Okay, let's unpack this a bit. Let's look at how they actually isolate that chaos, because the notes detail a very specific flow for a recent project.
Right, the data pipeline.
Yeah. So users interact with microservices, and then those microservices talk to Spanner.
Which is acting as the OLTP side.
Right. And then from there, data moves over to BigQuery, which acts as the OLAP side.
Warehouse, yeah.
Yeah, the data warehouse. And from there, it goes through business rules, then staging, fact tables, and finally to reporting. But let's pause at that initial divide. Spanner to BigQuery, OLTP to OLAP.
The separation of online transaction process and online analytical processing, it really comes down to the fundamental nature of the work being done on the data itself.
Okay, break that down for us.
So OLTP, which is Spanner in this architecture that handles the live real-time interactions, like when a user clicks a button to update their consent preferences on that management platform we mentioned.
Yeah.
That is a single rapid-fire transaction. Spanner is built to provide AC guarantees for those specific transactions.
ACD, meaning it guarantees data validity even if, say, the power goes out halfway through a save.
Exactly. It either all saves or none of it saves. You don't get any half-written records corrupting the system.
Got it. Atomicity, consistency, isolation, and durability.
You nailed it. And a system like Spanner, it heavily prioritizes low latency. It needs to process thousands of those tiny individual updates per second without skipping a single beat.
So going back to that restaurant analogy we started with, Spanner is our front of house staff.
Yes.
The waiters are taking these small rapid fire orders on a super busy Friday night. Table 4 wants a steak, table 6 wants a salad. Low latency is basically survival.
Right. They can't wait 5 minutes to write it down.
No, they need to write that order down instantly and get it to the kitchen.
Exactly. Now, contrast that with OLAP, online analytical processing, which in these notes is handled by BigQuery.
The back office.
Right. BigQuery is not taking individual orders.
Right.
It is designed for massive analytical queries. complex aggregations, scanning petabytes of data just to generate a single report.
Oh, wow. Petabytes.
Yeah, it's your back office manager sitting in a room at the end of the month looking at every single order placed over the last 30 days just to forecast next month's inventory.
And if they weren't physically separated, that nightmare scenario we started with actually happens.
Exactly. The manager crashes the dining room floor.
The live application basically freezes because the database is totally locked up trying to calculate like a monthly average or something.
Yeah, and what's fascinating here is that architecture at this level, it isn't just about connecting software together. It's about isolating different types of workloads.
Workload isolation, yeah.
The beauty of this divide is that BigQuery can crunch all those petabytes of data, running incredibly heavy reporting and business rule transformations without adding even a single millisecond of latency to the transactional processing of Spanner.
That makes total sense. So we have two completely isolated rooms, the front of house and the back office. But, and this feels like the obvious physical problem here, how do you actually move the data between them without breaking either system?
Right, because they are separate.
Yeah, the back office manager still needs those receipts somehow.
Moving data safely and reliably at that kind of scale is notoriously difficult. But the notes outline this really clever incremental loading strategy to solve this.
Using a control table, right?
Yes, managed by a control table utilizing a watermark.
Okay, so looking at the notes, the control table tracks the source of the data, the start watermark, the end watermark, and the status, like if it's running or completed. I'm assuming a watermark in this context acts sort of like a save point in a video game.
That's a great way to think about it.
Like if your character dies, you don't start the whole game over from level 1, you just load the last checkpoint.
That is the exact mechanism at play here. Because if you're copying data from Spanner over to BigQuery, copying the entire database every single night would waste just massive amounts of compute and, frankly, money.
Right, you'd be copying years of old data every day.
Exactly. You only want to extract the new data that arrived since the last time you checked. So you place a watermark, which is usually just a timestamp. You establish that, hey, we have successfully copied everything up to Tuesday at 5:00 p.m. So the next time the pipeline runs, it only queries for records created or modified after that exact timestamp.
And the notes have a very strict golden rule attached to this, which I loved. They state, advance the watermark only after successful completion. On failure, reuse the last successful watermark.
Yes, and that strictness prevents permanent data loss. Think about it. If a job is running and the system crashes halfway through, advancing the watermark would trick the system into believing that batch was fully loaded.
Oh, I see.
You would forever have a hole in your analytics.
Yeah.
So reusing the last successful watermark ensures restartability.
Wait, hold on. Let me push back on that for a second.
Sure.
Let's say I'm transferring 1 million new rows, and the job crashes at exactly 500,000. Reusing the old watermark means I start over from 0 on the next run, right? So won't I accidentally load those first 500,000 rows a second time? I feel like I'm going to create massive duplicates and completely corrupt the analytics. Suddenly it looks like we had twice as many credit card defaulters this week.
Ah, okay. This raises an important question, and honestly, you just hit the exact trap that catches a lot of junior engineers.
Really?
Oh, yeah. How do you restart a failed job from the beginning without double counting the data that already made it across before the crash?
Exactly. How do they fix it?
The architect's notes introduce the solution to this, which is a really vital principle in distributed systems called idempotency.
Idempotency. Okay, I always think of that like flipping a light switch, right?
Yes, exactly.
I can flip a switch to the on position 10 times in a row, but the light doesn't get 10 times brighter. It just stays on. The state is guaranteed regardless of how many times the action is applied.
That's spot on. Reprocessing must not create duplicates. And the notes list several ways to achieve this, like partition overwrites or delete and insert combinations, but they actually give us a concrete look at how they implemented this using CDC.
Change data capture.
Right.
The logic they laid out for CDC here is just incredibly tight. So you build a transform staging table with the incoming data.
Yep.
Then you compare that staging table with the final target table using a merge statement. But the key is they emphasize comparing only the business columns.
Yes, you intentionally ignore the system metadata because the exact millisecond a row was copied from one database to another. That's always going to be different, even if the user data is totally identical.
Oh, right, because it's new run.
Exactly.
Yeah.
So you only compare the actual business reality, the consent status, the user's address, their account balance.
So the 3 conditional rules they programmed make perfect sense then. Rule 1. If it is a new business key, like a user we have never seen before, you insert the record.
Simple enough.
Rule 2. If it is an existing business key, and the business columns have actually changed, say they updated their consent preference, you UP-gate the record.
Right.
And rule 3. If it is an existing key, and the business columns are completely unchanged, you do nothing.
And that right there is true idempotency in action. Because think about your failed pipeline scenario from earlier.
The one with the 500,000 duplicates?
Yeah. So the job restarts from the old watermark and pulls all 1 million rows again. It pushes them to the staging table. Now, the merge statement evaluates those first 500,000 rows that already made it across before the crash.
Right.
It looks at the business columns,
Yeah.
sees they're identical to what is already sitting in the target table, hits rule number 3, and simply drops them.
Oh, wow. It just ignores them.
Exactly. No duplicates, perfect restartability, and pristine data quality for the analytics team.
That is so elegant. Okay, so we have perfectly synchronized our data. The back office finally has all the receipts. But querying petabytes of data isn't exactly as simple as opening up a spreadsheet, is it?
No, definitely not.
If the whole point of this architecture is to allow massive analytics, how does the system not just crash when a user actually asks it a complex question?
For that, we really have to zoom all the way in to the anatomy of a single query.
Okay, let's do it.
We are moving from the macro architecture of the whole data flow down to the microscopic execution engine. And the notes center this entirely around the Hive driver.
Right, the Hive driver. Looking at its responsibilities here, creating the user session, maintaining the execution context, monitoring the query lifecycle, returning the results. I mean, it sounds like it doesn't actually process the data itself.
No, it doesn't touch the data directly.
It's just holding the clipboard like a general contractor on a building site.
If we connect this to the bigger picture, the driver orchestrates everything. It holds the session state, which, yeah, is basically the contractor's clipboard holding all the blueprints and the permits.
Yeah.
It knows your current database, your temporary tables, your specific session settings. But the real magic is the chain of command. It coordinates to translate a human question into a physical data retrieval.
Okay.
It starts with the user passing the query to the driver, and then the driver hands it off to the compiler.
And the compiler feels sort of like a translation layer.
Yeah, and it breaks down into 3 distinct sequential phases. So first is the parser.
The parser.
The parser is purely concerned with syntax. Like, did you spell select correctly? Did you miss a comma somewhere?
So it's just spell check.
Basically, it isn't looking at the data at all yet. It is strictly evaluating the structural grammar of your query.
The grammar check. Okay, and if it passes that, it moves to the semantic analyzer,
Yeah.
which the notes say performs metadata validation via the metastore.
Right, so the system is now checking reality. Your query might have perfect grammar, but if you ask for a column named, say, Revenue 2025 in a table that doesn't actually exist,
Right, that's a problem.
the system needs to know that before it starts searching petabytes of hard drives. So the semantic analyzer consults the metastore, which is just the directory of the entire database, and asks, does this table exist? Do these columns exist? And does this specific user even have the security permissions to read them?
Okay, so the parser says the sentence makes sense structurally, and the semantic analyzer confirms the things you are asking for are actually real and accessible.
I get that.
And then it hands it to the optimizer.
Yes, and this is where the real magic of big data happens. A cost-based optimizer is analyzing dozens, sometimes hundreds, of potential execution paths.
Oh, wow, really?
Because in a distributed system, data is scattered across thousands of physical machines. So the optimizer has to decide, should the system join table A to table B first, or table B to table C?
It's basically calculating the best route on a map.
Exactly. It looks at table statistics. So it knows, for example, that table A has 10 rows and table B has 10 billion rows.
That's a big difference.
Right. And it mathematically determines that pulling the 10 rows first and using them to filter the massive table is exponentially faster than scanning the massive table first.
Oh, that makes sense.
One route might take 3 seconds, another route takes 3 hours and burns thousands of dollars in compute power. The optimizer calculates the absolute cheapest, most efficient route before a single byte of actual data is even moved.
That is incredible. It calculates the most mathematically efficient execution plan, and then the compiler finally hands that optimized plan over to the execution engine.
The final mile.
The final mile, yeah.
So the execution engine hands the job to a resource manager. In these specific notes, that is Yarn, which coordinates the distributed cluster.
Right, darn.
It assigns tasks to processing frameworks.
Mm.
We often hear terms like MapReduce or TES for this.
Mm.
And conceptually, think of this as needing to process a massive boulder.
Okay, a boulder.
Instead of one machine trying to crush it all by itself, these frameworks break the boulder down into a million tiny pebbles, hand a pebble to a million different worker nodes simultaneously across the distributed file system, have them do the math locally, and then send just the answers back.
Oh, man. So all those answers flow from the worker nodes, back to the resource manager, back to the execution engine, and finally, all the way up to the driver, which hands it to the user.
You got it.
It is staggering when you think about it. Every single time you pull analytics on a massive data set, you talk to the contractor talks to the architect checks the permits, calculates the most mathematically efficient route, hires 1,000 workers to break down a boulder, and hands you the result, usually in just seconds.
The wild, right? And these notes showcase a professional who fundamentally understands every single mechanism triggering underneath the keyboard.
Right, they aren't just guessing.
No. And when you understand the engine to that degree, you can optimize it. You can explain to a business stakeholder why their specific query is slow, or how moving to a different table structure will actually solve their reporting bottlenecks.
So, zooming back out a bit, this single document really took us on quite a journey today.
It really did.
We started with the highest level strategic business need. You know, the absolute necessity of separating live, breathing transactions on the OLTP side from the deep, heavy analytics on the OLAP side.
Crucial foundation.
Then we explored the idempotent plumbing of watermarks and changed data capture to move that data safely between the two worlds without creating massive duplicates.
Right.
And then we zoomed all the way into the engine room to watch a Hive driver coordinate an incredibly complex sequence just to answer a single question without crashing the whole system.
It's a powerful reminder that at the highest levels of tech, it is never just about listing the tools you know. I mean, it's about understanding the flow of information. It's about applying logical, step-by-step problem solving to tame chaotic systems.
Yeah, you really have to understand the chef's philosophy, not just read the recipe. Whether you're prepping for your own major interview or you are just trying to understand the invisible, sprawling architecture that powers almost every modern app on your phone.
You know, looking back at that CDC logic, the change data capture rules we discussed,
Yeah, the 3 rules.
there is actually a really fascinating philosophical question hidden in there.
Oh, really? Which part?
In the rule about unchanged data, the notes explicitly state that when the system compares the live data to the warehouse data, if the business columns of a record are found to be unchanged, the system should do nothing.
Right, it drops the record.
Exactly. This is standard industry practice. It saves massive amounts of storage space and compute power. It keeps the system incredibly efficient because you aren't rewriting what is already there.
The idempotency rule we talked about?
Right. But in our modern, hyper-data-hungry world, we are constantly trying to understand user behavior. Right?
Oh, definitely.
We track every click, every movement, every preference update. So isn't the fact that a user's status didn't change over a specific period of time actually a highly valuable piece of behavioral data in itself?
Oh, wow, the silent data.
Exactly, the silent data. By choosing to do nothing and discard that non-event purely to save space and processing power, are we inadvertently throwing away hidden insights about system stability or user hesitation or long-term habits?
That's a wild thought.
The absence of an action is still an action. It is definitely something for you to ponder next time you consider what data is truly valuable.
I love that, the silent data. Well, it turns out reading someone else's messy, brilliant notes is a pretty good way to spend some time. Just remember, the next time you're sitting in a restaurant and you hand your order to the waiter, there is a whole universe of architecture making sure the back office manager gets the receipt.